Good afternoon. I am Chanda Devnath, one of the PMRF fellows. So I am the TA of this course named Retrosynthesis and some problem solving approach. So here in these classes I usually discuss about some organic reactions which may help you to plan retrosynthesis of any compound. So in the last classes I was discussing about rearrangements. So one or two has been remaining, so I will complete that. Then we'll move to a new topic that is called name reactions. So here we'll discuss about different type of name reactions, and I think if you covered most of the name reactions, then it is very easy to predict a retrosynthesis of any compound. So in the initial 6 to 7 classes we will discussing about all these different reactions. Then after that we will take some important molecules and design the retrosynthesis and how to design a retrosynthesis of those compounds. By getting an idea about all these types of organic reactions, it will help you to attempt your assignments and also the upcoming examinations. So let's start. So in the last few classes I was discussing about the rearrangement reactions. We are almost done. 2 or 3 are remaining. This one is diene phenol rearrangement. So here in this case a diene rearrange to a phenol. That's why it's called diene phenol rearrangement. So if the reaction is catalyzed by acid. So if you see the mechanism, in presence of acid, this oxygen molecule take this proton and get activated. Then this double bond shifts to here. Generating a carbocation at this place. After that, this R group shifts from 1 to shift and transferring the carbocationic center at this carbon atom. Then it undergoes aromatization and get our product, that is phenol. This is called dienol phenol rearrangement. Next one is Semler-Wulf reaction. In this reaction, this hydroxin sorry, except one second. In this reaction, oxime of a cyclohexanone with in presence of acid rearranged to give us aniline. This is a one type of I have already discussed about the Beckmann rearrangement. This is a side reaction or the exception of Beckmann reaction. If in case of Beckmann rearrangement, what we have learned, suppose this type of compound is given. Okay, just try to find the difference between Beckmann and this Semler-Wulf reaction. So what we do in case of Beckmann reaction, if it is get catalyzed by acid, this OH will take this proton and this will eliminate, and this anti-bond will migrate to nitrogen, generating a 7-member ring. With the carbocationic center here. After that, a water molecule attacks. To this place, and through elimination of water, it generates amide. Okay, this is Beckmann rearrangement. We have already discussed about it. This is Beckmann rearrangement. Now see the difference between this Semler-Wulf and this Beckmann rearrangement. Now in case of this alpha beta unsaturated type of cyclohexanon, so they have mentioned it has to be cyclohexanon. So if there is a alpha beta unsaturated, if there is a double bond at this place, then in that case this type of migration does not take place. Before that, before this migration can be possible, this double bond migrate by itself because it is in conjugation. So what happens after deprotonation of this OH group, this at H will take part in a conjugation, will come here and double bond will shift to this nitrogen, forming this type of agitating type of intermediate. After that, it undergoes again a rearrangement and we get this as our product. And through aromatization, we get a amine. Okay, so whenever there is a double bond in a ring, instead of Beckmann rearrangement, there is a possibility of Semler-Wulf reaction. Okay, so try always see the options and always. Okay, so I hope it's clear. There is a question: what will be the product? So they have added DAST and in presence of DCM minus 78 degree. DAST is a fluoride source. You can consider it as just like a F minus. You can consider it as a nucleophilic donor of F minus. It just give a F minus. So what will be the reaction? From the structure of this oxime, so you can predict it may go through a Beckmann rearrangement or whatever we have discussed just, that is Semler-Wulf. And there is another probability while discussing about the Beckmann rearrangement we have.
Hello?
Yes?
Hello?
Uh,
Yeah, I'm probably disturbing you. I can't see any slide. Are you showing any slide?
yeah, it was okay. Then somehow it got disconnected. Okay,
Yeah, I can't see anything. Maybe my problem and your problem, I don't know. Please check it.
Sorry, it has been disconnected. Is it visible now?
Yes, now it is visible. Thank you so much.
Yes,
Thank
ma'am. It is visible.
So I will just give a recap. I was discussing in the last few classes, I was discussing about the rearrangement reaction. So we have almost completed all the topics. So some few are remaining. The first one is this dienol phenol rearrangement. So where it get catalyzed by a acid. So in presence of acid, this dienone get catalyzed, and after that, through conjugation of this adjacent double bond, there is a carbocationic center here. Then this adjacent R group migrates, shifts from, then through H plus elimination, like aromatization, we get this phenol. Next, we have discussed about this Semler-Wulf reaction, where this oxime can be converted to amine in presence of H plus. So this is a extension of Beckmann rearrangement. So I have shown already that what is Beckmann rearrangement. In case of Beckmann rearrangement, the simple oxime get catalyzed by H plus, and through migration of this ringed bond, we get a amine. Now this is the extension of Beckmann rearrangement. Suppose we have a double bond in the ring. We have already a conjugated double bond in the ring. What will happen? In that case, instead of migration of this adjacent carbon-carbon bond, this double bond migrate itself. So after protonation of this OH, this becomes a good leaving group, and this adjacent allylic H plus migrates from this place, and this double bonds shifts to this nitrogen atom, forming this azididine type of intermediate. After that, through ring bond cleavage of this strained three-member ring, we get this intermediate, and through aromatization, we get our amine as our product. Get the amine as our product. So this was question I was discussing about. Suppose this substrate is given and we have added DAST, that is a diethyl aminosulfur trifluoride. You can consider this as a nucleophilic source of F minus. It's a very sensitive reaction because it's a highly active nucleophilic, it's provide highly active nucleophilic F minus source. So if you add this one, it will create a F minus and it will attack. So its storage is, you have to store it in a very cold temperature. So the reaction is also at a very low temperature because the nucleophile is too much reactive. Because this nucleophile is too much reactive. So suppose this is given, and what will happen? So there's a, from the oxime type of structure, you can get idea there can be probability of Beckmann rearrangement. Now I have already discussed about Semler-Wulf. That is also a probability. There's another probability of Beckmann fragmentation, which I have already discussed while discussing about the Beckmann rearrangement. When Beckmann fragmentation takes place, during I've said when the migration of a carbon-carbon double bond is slower than the breakage of the carbon-carbon double bond. What I mean, suppose, so this is the model structure for Beckmann rearrangement. Okay. Now what do you know? In that case, Beckmann rearrangement, this anti-bond shifts and this get eliminated. Okay. Suppose now this bond breaking and bond making taken simultaneously at a single step. Suppose this bond breaking steps is faster than the making of another new carbon nitrogen bond. What will happen in that case? So suppose you have this type of structure. Now in that case, if you just migrate this bond, that will give a simple Beckmann rearrangement. But migrating this tertiary carbon atom, because this is, suppose there are just two hydrogens, so this carbon atom is less bulky, but with two methyl group the carbon atom is bulkier than that of this one. So eliminating is shifting this carbon atom from this carbon to this nitrogen is slower than that of the breaking, just the breaking of this bond. So in that case, what happens? When there is a probability of a formation of a stable carbocation, and that is only possible when this carbon-carbon bond is highly substituted. So if there is a formation of a stable carbocation, in that case, instead of shifting of the carbon-carbon bond, there will be just a break. So what will happen? It will generate a carbocationic center at this place and a triple bond here. This also gets eliminated. Okay. So then if there is a nucleophile or water if in the medium, that nucleophile will attack to this carbocationic center. So here the similar type of scene can take place because this is highly substituted carbon atom. So this, after this will come here and get eliminated from the system. Generating a benzylic as well as tertiary carbocation. So you know the benzylic carbocations are stable. Also they are tertiary, so it is also stable through hyperconjugation effect. So this carbocation is stable because of the Plaza effect of this methyl group, hyperconjugation of the methyl group, and also the resonance of this phenyl group. Because of this carbocation is highly stable. After that, this F minus will attack to this carbocationic center. And we will get this as our product. Okay, let's go to the next question. So this is another last one. This is Phi's rearrangement which is remaining. So in the last few ones, we whatever rearrangement we discussed, that is 1-2 rearrangement. Usually the rearrangement takes place from the adjacent carbon atom to adjacent nitrogen or carbon atom. So that is called 1-2 rearrangement. But in this case, this rearrangement is one carbon ahead is also possible. So a Fry's rearrangement reaction of a phenolic ester to a hydroxyl aryl ketone by catalyzed by Lewis acid. It involves a migration of a acyl group and the reaction is orthoparaselective, and one of the two products can be favored by changing the reaction conditions such as temperature or the solvent. So let's see the mechanism. So in this case, if this phenolic ester get catalyzed by a Lewis acid, after that it undergoes generating a carbocationic center here, generating a carbocationic center here. After that, this O minus comes here and it can attack from this ortho position or this para position, giving us these two as a product. And as para attack is more favorable, so at room temperature we get this para product, and in case of in high temperature we get this ortho product. Why this para attack is more favorable? Because this O minus is already coordinated with this Lewis acid. This is large aluminium with a 4 chlorine, the 3 chlorine atom. Because of that, this ortho attack is less favorable because of high steric hindrance. That's why at room temperature it always gives a para product. If you give a high temperature, then it goes to the, instead of kinetic product, it will give a thermodynamically stable product, because this product has stability from the hydrogen bonding. This product has structural stability from the hydrogen bonding, but it has a steric hindrance instability. Because of that, the reaction, the product is stable. The ortho product is more stable than that of the para product according to thermodynamics. But because of the steric hindrance, the para product will form faster than that of the ortho product. So this is called kinetically controlled product, and this is called thermodynamically controlled product. You understood, right? Whenever the product is more stable but it forming at a later state, that is called thermodynamically controlled product. But whenever the product is not that much stable but it forming faster rate, that is called kinetically controlled product. Because it is kinetically stable, so it's forming at a faster rate. Okay? So let's go to the next topics we will discuss. So next we will discuss about some important name reaction. In your assignments you have here you have got this type of name reactions again and again. So if you know what are these name reactions, it will be easier for you to attempt those assignments, as well as to get an idea how to predict a retrosynthesis of a compound. You should know the basic single reactions, so that by combining all the reactions you can predict retrosynthesis of any large molecules. So before going to the retrosynthesis, we will just try to solve a simple small reactions, so that you can get an idea how to combine them and we can plan a formation of a large molecule. So there are different type of name reactions. We will discuss one by one. So I just mentioned some of them. There are many more. So I will try to cover almost all the important name reactions. So let's start. First one is aldol reaction or aldol condensation. This is very easy. We have already studied it in our plus 2 and from plus 2. So what is aldol reaction? Suppose if aldehyde is given and we have added base, a dilute base or dilute acid. Suppose an aldehyde is given, so not aldehyde, say aldehyde or ketone with at least one alpha hydrogen. Aldehyde or ketone at least one alpha hydrogen. At least one alpha hydrogen. So in presence of acid or base, what happens? It will take one proton from here, forming a enolate. Then you add another molecule of aldehyde or ketone. This will come here. This is called aldol reaction or aldol addition. Okay. Now, sorry, I have missed one carbon. Now, if there is another H is available, it will undergo the dehydration reaction and you will get this aldol condensation product. The simple addition, then if there is any another molecule, another alpha hydrogen is available, it can undergo the condensation reaction. Next one is Michael addition. If you have a alpha beta unsaturated compound and if we add a nucleophilic source, it will, instead of attacking to this electrophilic center, due to high conjugation with this carbonyl compound, this carbon atom also has a electrophilic center. So instead of this carbonyl compound, it attacks to this beta carbon. This is called Michael addition. This is called Michael addition. The nucleophile is called Michael donor and this alpha beta unsaturated compound is called Michael acceptor. So let's solve some questions based on these two name reaction. Then we'll try to get an idea how we can apply these reactions to predict the retrosynthesis of any compound. What will be the product in these two reactions? So from the name it's a simple aldol reactions. So as there is no other molecule of aldehyde is given, so we'll consider that there is two molecule of the same aldehyde we will consider. Two molecule of the same aldehyde we will consider. So first we have to find the alpha hydrogen. So this is called alpha hydrogen. So in presence of base, it will be eliminated and it will generate a negative charge here. After that, it will attack another molecule of aldehyde. And these get open up. Okay, so if you had one molecule, if you just eliminate one molecule of water from this place, it will give us the condensation product, that is a alpha beta unsaturated aldehyde. Okay, the similar thing will happen in this case also. If there is alpha hydrogen, where is alpha hydrogen? Both the centers are, both the alpha carbons are equivalent, so you can take proton from one of them. So just consider two molecule and you will get this as our product. Okay, we will get this as our product. Mechanism is similar, so I am not drawing it again. Next one, how will you plan the retrosynthesis of this compound? So obviously, as I am discussing about aldol reaction, so aldol reaction will be one part of them. So what will be the retrosynthesis of this compound? So we know this type of compounds can be prepared through retrosynthesis if you just cleave along this alpha bond. What is the probability? So what is the synthetic equivalence? As negative charge at the alpha carbons are stable, so we are keeping negative charge at this place, and as oxygen is attached to this carbon, so we are keeping positive charge at this place. So these are these two synthetic equivalent. So what are the synthon? Aldehyde, and this can be simple cyclopentanone. So the forward synthesis you can plan easily. It's a simple aldol condensation. You will just take a proton from this alpha carbon. This will attack to this aldehyde center and open up to give us this as our product. Okay. Let's go to the next question. What will be the correct answer for this reaction? So suppose this is A, B. What will be the product of this reaction? I just give 5 seconds. Just think. So simple aldol reaction will take place. There are two aldehyde center, and as they, in this case there are two ketones, so there are two alpha carbon. One is this one, another is this one. So we can take a proton from this at this place as well as at this place, and after elimination of both the proton, this carbon center can attack to this aldehyde center. So the product will be so after elimination of, there will be a wedge. So after elimination of water, as there is another alpha hydrogen is available, so this will come here. So after elimination of two molecule of waters, so the correct option will be option B. Correct option is option B. Okay. Let's go to the next question. Provide the method using aldol reaction. So this is again the simple one. We just have to break along this double bond. So and we're just breaking one bond, okay, the double bond. So what will be the synthetic equivalent? So after breaking this double bond, we are keeping a negative charge here because it is adjacent to alpha carbon, and a positive charge here. Adjacent to alpha carbon, the negative charge is always stable than that of positive charge. So we are keep after the synthetic equivalent will be like this, not the opposite one. So this is our synthetic equivalent. After that, if you now to satisfy this positive charge, there should be a leaving group. There should be a leaving group. So the synthon will be kind of like this. And there is a H plus. Okay. After that, if you break this double bond again, if you break this bond also, now as OH is attached, so a positive charge at this center will be stabilized by this OH. So we are keeping positive charge at this carbon and a negative charge on this carbon. Okay, so now it can be aldehyde, and this can be also. So here you can see by using just simple aldol reaction, we can predict the retrosynthesis of this compound. Next is provide the method using aldol reaction. So you have to provide a method using aldol reaction. Now see, there is a difference. If you just think that this is also a 2 molecular aldehyde, but it is not adjacent to the carbonyl. So this is not at the beta carbon. This is not at the this carbon-carbon bond has formed at is not at the alpha carbon. The carbon-carbon bond has formed at the beta carbon. So if you break this one, so the now in this case the synthetic equivalent will be bit different. Now if as you have broken this bond, now this one is not at the alpha carbon. This is the beta carbon according with respect to this carbonyl atom. This is alpha. This is beta. So we know that positive charge at beta carbons are usually stable than that of the negative charge. So if you keep a positive charge here and this carbon is at alpha carbon, so you can keep a negative charge at this place. Okay, so what will be the synthetic synthon for this two? So simple H plus, if you add a H plus, we can get this 1,2 diketone type of compound. Next, to satisfy this positive charge, what will be the synthon for this one? If you just eliminate this H, it can be a alpha beta unsaturated ketone. So you can get an idea about the forward reaction. So this will be a Michael addition. This will be a Michael type of addition. Now, to prepare this one also, we can use to prepare this one also, you can use aldol reaction. If you break the bond at this place, so I put a CH3 here. Okay. So this is prepared through aldol reaction, and this after that this alpha beta unsaturated cyclopentanone get conjugated with another molecule of this diketoaldehyde, then it get this Michael addition product. Okay, let's go to the next question. What will be our A, B and C? In all the cases, LDA is given. LDA is a base. LDA just consider is a base, aluminum based base like butyl lithium or something. What will be the product A, B and C? So let's just give a hint that obviously there is a alpha hydrogen here. So it will take a alpha hydrogen from this at this place and it will form a enolate. After the formation of enolate, it will react with all the three types of electrophile. This is also electrophile. This is also electrophile aldehyde. This is acyl chloride and this is a allyl bromide. So it will react with these three types of electrophilic electrophiles. So what will be the product? I just give 2 seconds. Just try. So what will be our first step? First it will form this enolate. It will form this enolate. After that, it will react one by one. Suppose in case of A, it will react with this acyl chloride. So the product will be it will simply just attack and remove the chlorine atom. So the product will be this diketone type of compound. So the correct option will be this one. So these two are already cut. These two are already cut. 1 and 4 are already cut because the correct option is this for A, between A. Now let's see the B. So what will be the B? This is our A. Now if it attacks to this aldehyde, it will be simple aldol reaction. Aldol, if it attacks to this, it will be a double bond here and methyl. It will be a simple aldol condensation mechanism. I hope you will get an idea because you have solved many more questions based on this. So I'm just jumping to the answer. So this will be our B. So both of them have same B. So the deciding will be option C. Sorry, the deciding will be what will be the structure of C. So if we attack to this, if this attack to this allylic bromide, it will attack to this carbon and it will eliminate this bromine from the system, giving this as our product. So the correct option is option 3. It will be A, B and 3. Okay. Let's go to the next one. So we have to predict the synthesis of this cyclopentanone from this butane based compound. So you have to predict the synthesis of this compound. So let's go to the answer. So first, this ketone will take a proton from this acid. After that, this double bond will, this carbon-carbon bond undergoes a cleavage and it will shift to this, generating a carbocationic center here. After that, it undergoes a simple deprotonation reaction from this alpha hydrogen and it will attack to this carbocationic center, forming this cyclopentane type of ring. Then through elimination of a water molecule from this, using this alpha hydrogen, we get this cyclopentanone type of ring. So this reaction from the product, it may seems very difficult, but it's a simple reaction just catalyzed by a simple acid. I hope it's clear. So this is, suppose we want, what happens if instead of simple acid we provide a chiral acid in case of aldol reaction. What will be the scenario in that case? So scientists came up with, like, if you want to prepare a chiral type of compound, that is an enantioselective compound, just if instead of a chiral instead of a chiral acid, simple HCl or benzoic acid, if we add a chiral acid, this is pyrrole based, proline based acid. If we add this type of proline based acid, what will happen? So in that case, in the first step, what will happen? This In the first step, this proline will attack to this carbonyl center and form this imine type of structure. First it will form this type of imine type of structure. After that, this alpha hydrogen will be taken up, forming his enol type of system like this. Now when it will attack, the question comes for attacking the second molecule of aldehyde. It due to hydrogen bonding with this adjacent acid group. As this adjacent acid group is above the plane, this compound will be form a hydrogen bonding above the plane. So this suppose just try to imagine in a 3D model. Okay, this acid is above the plane. This acid is above the plane. So when it forms a hydrogen bonding with this ketone, it will be like this way. With this aldehyde, it will be forming a hydrogen bonding like this. So this upper phase is already blocked because this is already coordinated with this one. So the attack is only favorable from the below the plane. Attack is only favorable from the below the plane. So the OH will be open up. So this newly formed OH will be above the plane. So newly formed OH will be above the plane. So the correct option will be this one, where this newly formed will be above the plane, and we know always this anti product is always stable, so it will be anti, but newly formed OH should be above the plane, and to keep the anti arrangement, the previous methyl will go to the below the plane, forming this as our structure. Okay, I hope it's clear. Suppose just consider this acid group. As this acid group is above the plane, it is been connected to this aldehyde center through hydrogen bonding. So it is holding it from the above. It is holding it from the above. So the below phase is vacant for getting an attack or accepting an attack. Because of that, this OH will open up to the above the plane, and to keep anti arrangement, this methyl will be below the plane. Next there are some questions based on Michael reaction. So what will be the product in this case? What will be the product for this class? So first, there is negative charge here. So this will eliminate one of the bromine atom. This is simple actually substitution reaction. This is not a Michael reaction. Now as there is another molecule of now as there is another molecule of H is available. will eliminate the bromine atom and we get a cyclopropane type of ring. Okay. What will be the product in this case? This is also different a type of Michael addition. So this OH comes here. After that, as there is a H still available, so it undergoes a nullization again. So we get this as our product. Okay, let's go to the next one. What will be A, B and C? So first one is simple aldol condensation from as ketone is given and there is alpha hydrogen is available, and also heat is given, so it will be aldol condensation. That is also idea of if it will be aldol reaction or condensation. Whenever heat is provided, it will usually be aldol condensation. So the A will be, and in this case there is no alpha hydrogen is available, so the only this one will be take alpha hydrogen. It will act as a simple electrophile only. Next is if you add this Gilman reagent, the CH3 minus will attack to this beta carbon. I mean a methyl here. Next, a ethyl bromide has been added. If you add a ethyl bromide, what will happen? So as already a base source is already there, now among this proton and this one, which one is more acidic? Obviously this one is more acidic. So this will taken up and it will attack to this ethyl bromide. So the correct option will be like it will attack to this ethyl bromide. So this is our product. Okay. this is A, B, and this is our C. Let's go to the next one. What will be the correct option of this product? So in the first step, base is given. So obviously alpha hydrogen will be taken up. So between these two alpha hydrogen, which one is more acidic? Obviously this one, because it's adjacent to two carbonyl carbonyl group. It is adjacent to two carbonyl group. So this hydrogen is more acidic. This hydrogen is more acidic. Okay. So it will take a proton from here. So this negative charge will attack to this beta carbon, will attack to this beta carbon, will attack to this beta carbon. After that, then another molecule, if H3O plus is given, okay. So what will be the retrosynthesis of this compound? So suppose it will go through a, if you just break from this place, so one probability is like that, then this will be our ketone, and this will be our alpha beta unsaturated system. Then if you just do the another retro, This will be formaldehyde. To break from this place, and this will be simple ketone with a 5-member ring. There is another probability. If you break from this side, sorry, this one, this carbon, then alpha beta unsaturated ketone will be along this, and very simple. Next, if you want to prepare this one, this can be prepared. So both the methodology needs one aldol condensation followed by a Michael addition. So these are two probability. We can plan the retrosynthesis of this compound. So what is Robinson annulation? Robinson annulation combines which two reactions to build a ring system? So among these four options, which is the correct option? Aldol condensation and Diels-Alder reaction, Michael addition followed by intermolecular Diels-Aldol reaction, Claisen followed by aldol, or Manic followed by Robinson. Which one is the combination of which combination leads to the Robinson annulation? So the correct option is Michael followed by aldol condensation. Michael followed by aldol condensation. About this reaction we will talk about. So I gave a homework from that what we'll do if you want to do the epoxidation in a stereoselective manner. Now if you are given a double bond, you are forming the cyclopropane ring, that epoxide ring on it. Now the thing is, suppose you have given a double bond. Double bonds are planar because of the sp2 hybridized. Double bonds are planar. Now if you have given a double bond, now the question is from which place the epoxide will form. The epoxide will form from the above the plane, or epoxide will form from the below the plane. You're getting it right? If you think your double bond is in the plane, your double bond is already in the plane because of the sp2 hybridized, because these two carbon are sp2 hybridized, and sp2 hybridization means planar. So this double bond, both the carbons are sp2 hybridized. So this is totally planar. Now the question is, epoxide will form just above the plane or below the plane. So if you want to control the epoxidation of the double bond, the stereochemistry of the epoxidation, so to get that kind of problem, Sharpless came out with this strategy where Sharpless epoxidation reaction is an enantioselective chemical reaction to prepare 2,3 epoxy alcohol from primary and secondary allyl alcohol. So by this process we can form selectively by changing the nature of the reagent, just changing the nature of the reagent, we can control the stereoselectivity of the reaction. So instead of MCPBA, here we have to use tertiary butyl peroxide. This one, just MCPBA is this, metachloroperbenzoic acid. So MCPB is this is MCPB. Okay, this is hydrogen peroxide. So you can see the similarity of the structure. This is also a peroxide. This is also a peroxide, tertiary butyl peroxide. Instead of this peak group, we are using this tertiary butyl group. Okay, so here this tertiary butyl peroxide is doing the work of this epoxidation as similar to this MCPBA. Now the stereoselectivity of the reaction is controlled by this diethyl tartarate, this tartaric acid, diethyl tartarate. If it is negative, then we will get another one kind of stereochemistry. If it is positive, we will get another kind of stereochemistry. This is called diethyl tartarate. You know that diethyl tartarate, you know about tartaric acid? This is tartaric acid. This is tartaric acid. Okay. So this is tartaric acid. Now diethyl tartarate means instead of this COH there will be two ethyl group, CO2ET. Instead of this one there will be CO2ET. Okay. So if we use positive diethyl tartarate, we will get one kind of product. If we use negative diethyl tartarate, we will get another kind of product. So here the oxidizing reagent is tertiary butyl hydroperoxide, and the method relies on a catalyst formed from titanium tetride isopropoxide. So here titanium isopropoxide is acting as a catalyst which is controlling the stereochemistry, and diethyl tartarate. So this diethyl tartarate combines with this titanium isopropoxide and makes a stereochemistry which prefers the selective epoxidation. I am not going to the reagents here because it will be complicated for you. If you guys want to know more about this one, you can go and check Claydon in the asymmetric synthesis. There is a chapter, they have given this one, you can go and check from there. They have shown the active catalyst, you can go and check from there. I am not showing here, so I am just going to the problems and how we can approach to the questions and the tricks for those. Now the thing here, I have shown two examples. Suppose they have given this substrate, this allylic alcohol. Okay, the one point I have missed, for this type of epoxidation, sharp lip epoxidation, you can't perform sharp lip epoxidation on any alkene. That alkene should be an allylic alcohol. That alkene should be an allylic alcohol. This can perform sharpless epoxidation. But if you take just simple alkene, this is not can't be performed sharpless epoxidation. Okay, so this is one of the valid point, that for sharpless epoxidation your substrate should be an allylic alcohol. Without that, sharpless epoxidation is not possible. Now they have shown two examples. One is this one. Where they have added this titanium isopropoxide plus DMT. DMT is dimethyl tartarate. DMT is dimethyl tartarate. You have to use tartarate, any tartarate. It can be diethyl tartarate, it can be dimethyl tartarate, it can be diisopropyl tartarate. You have to use any tartarate. So they have used this positive dimethyl tartarate and tertiary butyl hydrogen peroxide. That's the short form TBHP, tertiary butyl hydrogen peroxide. This is the short form of this one. And in DCM at -20 degrees C after 16 hours, they got this one as our product. Whereas in this case, when they use minus diisopropyl tartarate in under same condition, they got this above one as a major product. Now how can we determine when this we will get this below product and when we will get this above one? So there is a trick. Suppose if you draw the allylic alcohol in this way, how I am showing, where this allylic alcohol will be in the right side, right above. To draw this one as a this way, you have to draw this only, then this trick will work. Okay, if you keep this allylic alcohol at this place and perform this reaction, in that case if you have given plus diethyl tartarate or DMT or anything, diisopropyl tartarate, you will give a wedge that is a positive, that is a above the plane epoxide. If you give negative, you will get a below product. Okay, so from that one you can, this is a trick. If you keep this allylic alcohol at the right side above, then whenever if you are given a positive diethyl tartrate or dimethyl tartrate anything, you will always get a above the plane product. If you are given a negative tartrate, you will always get a below the plane product. Now suppose if you have the reverse one, if allylic alcohol is in this plane, in the left side, what will happen? Just reverse of this one. If you use positive, you will give this below the plane. If you use negative, you will get above the plane. It was a short trick for examination purpose, because sometimes we get confused with the positive and negative, that what will be the product, because the transition state of this one is not possible to draw in examination or anyhow in a pen or paper. It is bit difficult because it's 3D and it's a very big transition state. You can go and check in Claydon. I think everyone knows about Claydon. Is a book, Claydon. You can go and check from there the stereochemistry if you want to know the transition state of this one. It is it's quite difficult. So this is a trick. If you want to remember it like this way, you can go for that. Otherwise, if you have any other strategy to remind this one, that is also okay. So suppose this product has been given, okay, and they have given positive, this positive diisopropyl tartarate, and other conditions are same. They have given TBHP, that means this tertiary butyl peroxide, TBHP, this tertiary butyl hydrogen peroxide, and they have given this titanium isopropoxide, what will be the product? So if we go through this tree, if we just turn it a bit and draw according to our easiest way. Then it will be like this. It will be like this. So as it is left hand side, and you are giving a positive, so what will be the product? The product will be below the plane. The product will be below the plane. So the epoxidation will be below the plane. Okay, now you can get it. The epoxidation will be below the plane. Now just answer what will be the stereochemistry of this one. In the similar way, if you just turn it, it will go left hand side, and as negative is given, so we will get a above the plane product. We will get a above the plane epoxide. Okay. About this reaction we will learn in the next class. So this much for today's. So I will just give an overview. So first we completed the rearrangement reactions, whichever is remaining. Then we started our different type of name reaction. We discussed about aldol reaction followed by Michael reaction. Then we solved some questions based on aldol as well as Michael reaction. Then we introduced the topic that is called Robinson annulation, which is a combination of Michael and aldol, which we will talk in the next class. It will lead to a formation of a ring structure. So this much for today's class.
Hello.
Yes.
Thank you for your lecture. This is a nice lecture. And the one thing actually, I missed it last class. Probably you have done that one last Sunday.
Yes.
Can I get PPT for that one?
Okay, I will upload that one. If you
Okay, okay. Thank you. Thank you so much.
Thank you.